Writing a proof in geometry can be a daunting task. Some students struggle with where to start, while others struggle to explain what they believe is just plain obvious. So in this video, I'm going to introduce you to a two-column proof and try and just explain to you how to construct one. So we're going to prove something that is fairly obvious. The goal is not to solve a difficult problem. It's just to provide you with an example as you embark on this journey into a new kind of math. Math with words. First, we're going to review some concepts and put them in our toolbox. An angle bisector is a ray that divides an angle into two congruent adjacent angles. This is a definition. This means that if it is stated in the problem that a ray is an angle bisector, then we can automatically, definitively conclude that the two adjacent angles that it forms are congruent. Congruent angles are defined as angles that have equal measures. Again, this is a definition. So if we conclude that a couple angles are congruent, then we can definitively conclude that they must have the same measure through the definition of congruent angles. Postulates differ from definitions. These are concepts that are so basic and accepted by the mathematical community that we all just agree that they're true without some kind of logical proof or justification. In fact, there isn't a proof for them. They just are. The angle addition postulate states that if point B lies in the interior of angle AOC, then the sum of the measures of angles AOB and BOC must equal the measure of the larger angle, angle AOC. Then we have properties. And properties are various rules. The ones I'm going to talk about now are algebraic rules that we can apply to geometric problems that include quantities. Two important properties are the substitution property of equality, which states that if A equals B, then either A or B may be substituted for the other in any equation or inequality. And the other is the transitive property of equality, which looks frankly a lot like the substitution one, but it's a little bit different. It states that if A equals B and B equals C, then A must equal C. The distinction here is that we're talking about an entire side of an equation equaling another side, that same side equaling a third side, and then we can basically get out the middleman and just say that the first thing equaled the last thing. And that's the transitive property of equality. So now that we've reviewed all of these properties, let's take a look at a common problem. So in this diagram, XZ, ray XZ, is the angle bisector of angle YXB. We also know that the measure of YXZ equals 58 degrees. And we're supposed to find the measure of the larger angle, YXB. Now, if you encountered this problem on a quiz or a test, you would be like, this one is pretty easy. Basically, since ray XZ is the bisector, then the larger angle is twice that of the smaller. So if I take 2 times 58 degrees, I would get 116, and I'm done. Well, with a proof, it's not about finding the answer. It's actually about displaying the logic that you use to find the answer, showing all of the accepted definitions, postulates, properties, and theorems that you used along the way. So let's see. How do we get from the given information in our problem to our solution? So let's put this given information on the left side of the screen, and we'll put the solution on the right, kind of make our way across. So what concepts did we use to get from here to there? Well, the first thing is this idea of an angle bisector. And we know through the definition that it creates two adjacent congruent angles. So we can write this. Now that we know that we have two congruent angles, we can use the definition of what it means to be congruent to conclude that these two angles have the same measure. Then, if you take a look at this other given piece of information, we can combine these two things and use the transitive property of equality to conclude this. And now we're going to go to our postulate, and through the angle addition postulate, we know that we can add these two angles and have the sum of their measures equal the measure of the larger angle. And then finally, with the substitution property of equality, we know that we can replace these two values for these two angles. And then through simple addition, we have our answer. Phew. Now to translate this into a two-column proof, by the way, that one's called a flow proof. What we want to do is we want to create two columns, the left one marked statements and the right one marked reasons. And then we're going to put all of our equations and given information under the statements column, and we're going to number them in logical order. And then we're going to put the names of the definitions, postulates, properties, and theorems that we used to make those conclusions on the right. And it's very important that you keep the numbers consistent. So anything that you've concluded, so let's say we concluded this on step 3, we need to say what definition or postulate that we used to make that conclusion on step 3 on the reasons side. And another rule is that your logic should progress from top to bottom. So if you want to use a piece of given information to make a conclusion, you have to make sure that you state it before you use it. Now, why do we go through all of this? What are proofs all about? And why do we really have to justify our logic in this way when the solution, frankly, is pretty obvious? Well, we're practicing like any skill, because when you get into higher level mathematics and you develop all these brilliant theories that no one's ever thought of, and you turn around and you need to explain them and justify them to your peers who have not yet thought of them, if you can't justify them through accepted definitions and theorems and methods, then they're just going to think you're crazy.